Hi, this is Ben. Today we're going to cover a very important topic in AP test, work and energy. There are three main concepts that I want to go through: the work-energy theorem, power, and conserved force with associated potential energy. Followed by these, we'll work through an example problem of a swinging pendulum. The work-energy theorem takes the form of the following: 1/2 mvf squared equals 1/2 mvi squared plus sum over f dot delta x, where f is the average force the mass experienced in the interval between x and x plus delta x. We can associate the first two terms as kinetic energy and the last term as work. This general form looks a little bit complicated, so we start with one-dimensional motion to get some physical intuition. We start with the following kinematic equation with constant acceleration in 1D. So we have Vf squared equals Vi squared plus 2a times xf minus xi, where f denotes final and I denotes initial. Multiplying both sides by 1/2 m gives us this form, which then we can identify to be kinetic energy final equals kinetic energy initial plus force times the displacement. This equation that we just wrote down already has the right form of the work-energy theorem. However, in general, force and its associated acceleration need not be a constant throughout the entire process. So let's consider a more general process where now acceleration a is a function of distance that looks like this. With a1 in the segment between x1 and x2, a2 in the segment between x2 and x3, a3 in segment between x3 and a4, so on and so forth. And we're supposed to define the velocity at x1 and x2, so on and so forth, to be v1, v2, so on and so forth. With those, we can write down 1D kinematic equation of motion that tells us v2 squared equals v1 squared plus 2a1 times delta x1. Using the same algebraic technique as the previous page, multiplying both sides by 1/2 m, we can transform that equation into kinetic energy 2 equals kinetic energy at 1 plus f1 times delta x1. Repeat this analysis for all n segments, then we can write down an equation that looks like this. And we can sum over all the equations that allow us to perform a bunch of cancellations, which left us with kinetic energy at n plus 1 equals kinetic energy at 1 plus this summation. Identifying kinetic energy at n plus 1 to be kinetic energy final, then we can rewrite this equation into a more general form that looks like this. Kinetic energy final equals kinetic energy initial plus sum over this quantity of f times delta x. Having written down the generalized form in 1D, now we can further generalize the work-energy theorem into higher dimension by promoting x, v, and a from scalar to vector. For a general path that meanders like this, we can break it down into discrete small segments delta x1, delta x2, so on and so forth to delta xn. And we proceed by writing the kinematic equation of motion into its vector form, where we have vector num square here and here, and dot product here. For those of you who are not familiar with this expression, you can refer to the video lecture that discusses about kinematics. The rest of the derivation uses the same techniques that we have used several times, where we multiply both sides by 1/2 m, which gives us a form that relates kinetic energy to f dot delta x in each segment. And then by summing over all these equations that we have for each segment, we can perform all these cancellations again, which ended up giving us the final kinetic energy equals the initial kinetic energy plus this term of summing over delta x, f inner product delta x, where that we can identify as work. So we obtain the full form of the work-energy theorem now. There are three important consequences of the work-energy theorem that I want to bring up. One is the separability. Oftentimes, there are multiple forces present in problems we deal with, for example, gravity and normal force, friction, and so on and so forth. In those cases, we can actually calculate the work individually and add them. To see this, we can identify, for example, F to be equal to sum of two constituent forces, F1 and F2, and write down the expression of work like this, which can be written as sum over these two terms, which is exactly the work done by F1 and work done by F2 respectively. 2. When the force is perpendicular to displacement x, it does not do work, because the dot product of the two vectors is 0 when they're orthogonal. This concept is useful in analyzing circular motions because now we know all the centripetal forces never do work. 3. When the force is constant, the work is only a function of the initial position xi and the final position xf. For all the paths that has a particular fixed starting point and ending point, for example this path versus this path, the work is always the same. This motivates our later discussion about conservative force. Second topic of the lecture is power. Power is the rate at which work is done. To obtain a more useful expression of power, we can write down an expression work, which allows us to write down P as F dot V. Power has similar properties as work, where one, we can also decompose power done by its constituent forces, thus it also has separability. And two, when force is perpendicular to velocity, there is no power done. And for the last part of the concept, we'll talk about conservative force associated with potential energy. As we previously established, when the force is constant, the work is only a function of final position and the initial position, independent of the path that the mass travels. In general, when the work done is independent of the path, the force is called conservative. Back to this previous equation, we can rewrite that into the form that looks like this, where the left-hand side only concerns the final configuration of the system, and the right-hand side only concerns the initial configuration of the system. By further defining the potential energy to be minus F dot x, we can rewrite that in the form of a conservation law, where the final kinetic energy plus the final potential energy is equal to the initial kinetic energy plus the initial potential energy. This is the energy conservation law that some of you might have seen. Take the example of gravitational force F equals mg. The potential energy takes the form of mgz, where z is the height. So gravity is conservative. An example of the non-conservative force is friction, where F dot v is always negative. So if you wander around more like this before you arrive at your final destination as opposed to just go straight, you get more negative work done by the friction, so there is no potential energy associated with friction because the work is path dependent. In the final part of the video, let us go through a pedagogical example of a pendulum. The mass is connected by a string hung at an angle theta. Initiate rest. And now you're asked to calculate its velocity when it swings through theta equals 0. Some of the keen audience might say, oh, you convert potential energy to kinetic energy, done. But here I want to go step by step in explaining why you can do that, as you actually have another force in action, namely tension. If we examine the free body diagram and the direction of travel at any given theta, like this, we can see that the total force is the sum of tension and gravity. As this object is undergoing circular motion, the velocity is always perpendicular to a string, which means that the tension is always orthogonal to the velocity. After finishing the free body diagram analysis, we can proceed to solve the problem by writing down the work energy theorem looks like this. And using the separability property of the work, we can write the total work as the work done by tension and the work done by gravity. And as we previously established, tension is perpendicular to the direction of motion, so it does not work. It does zero work. So the change in kinetic energy is only due to the gravity, which from our previous analysis, we can decompose into gravity times the vector connecting the initial position to the final position, which is basically the potential energy difference. And then we can obtain the final answer that looks like this. So that covers the conceptual part of the work and energy theorem. And in the next video, we'll go through more examples to get us more familiarized with tackling test problems. Thanks for tuning in, and until next time.